Can y'all see that?
Looks good.
Yeah. Cool. Yeah. Right, here you go.
All right. Uh, just want to apologize for all the mishap that's going on. It's been a little crazy. Thank you for all coming to our critical design review. This is for IREX 2025, our new rocket Phoenix. If you were with us at PDR, you'll notice a lot of changes. But let's hop right into it. All right. So uh, today, this is our agenda for today. We'll be updating you on the project, everything that all the changes that have happened to the team, all the changes that have happened to the scope of the project. We'll be going sub team by sub team, and then going into testing that we have done, testing that we will do, and at the ending we'll have questions. So I've highlighted for y'all the changes. You may recognize some faces. You may see some new faces. There's been a leadership change since PDR. Myself, Alfredo Hernandez. I'm now a chief engineer. My project manager, Isabella. We have two new propulsion leads, and we have a new recovery lead. So this is a breakdown of our structure. It's very standard, very similar to past years. Our flyer of record, Randy, has been mentoring us, and we have not listed here so many alumni mentors who have been so helpful to us.
Moment we have 23, at least those men and 7 women. I also want to point out that we have 3 members. We have 5 members with their L1 certification. Before competition, we expect to have at least 2 more for each, 2 more ham radio license, 2 more L1 certifications, as well as 2 new L2 certifications. And in fact, we have about 6 members that are working on their L1 certification and expect to launch next Saturday at Hearn. A little bit of what's been happening the last 2 months. Most of you were here or watched our preliminary design review, which was about 2 months ago, where we presented a very different project. It was for the 30K COTS category named Sasha. And we received a lot of feedback on that project, and that led to some meetings with our mentors where we evaluated our options. One of them was related to the Lone Star Cup. The Lone Star Cup was an event organized by some of the other, all of the Texas teams. And that happened a couple weeks ago. We did not participate because we wanted to focus all our efforts into this project. And in order to do that, we have also switched categories to the 10K COTS and have scaled back a little bit on our SRAT projects. As part of those changes, as Alfredo mentioned, also leadership restructure. We have a new project manager, myself, as of February 28th, and a new chief engineer as of March 7th. And that week also, our new leads for propulsion and recovery. And during this whole time, we've been developing our project for the 10K COTS category, our rocket called Phoenix. And that leads us to today, where we have our critical design review with a design that is mostly finalized, and we're getting ready for continuing manufacturing and documentation.
Isabella talked about the changes in scope. Given our time frame, we've thought it wise to switch down to 10K COTS. We are a new team, and so we'll be working back up. But right now, with the time frame, with the new team, we thought it'd be best. This makes manufacturing a lot simpler. We can reuse a lot of parts from Shasta and repurpose them. We are not using air brakes anymore. That was something that was presented in the PDR. They are out of scope. The capstone team that's on that did a great job, but uh, integrating it in the time frame, we didn't feel that we'd be able to do it justice. So the goals for this project, we are going to get a rocket off the rails. There's gonna be a lot of hands-on learning. There's gonna be a lot of mentorship, a lot of building up with the team. A lot of this project is built around repairing, reusing, repurposing old components.
As some of you know, the competition is the second week of June. So that puts us with a very accelerated timeline, which we've talked about a lot. Um, we have a good idea of what the next 2 months are going to look like. Most of April is going to be, firstly, the first 2 weeks after this, we're going to be taking in all the feedback that we receive and implement that. And starting next week, we expect to have all our major purchases finalized, as well as beginning our team and competition logistics. And then we are going to finalize on the critical testing, specifically related to recovery and avionics. And we expect to have manufacturing completed around mid-May or maybe the third week of May. During this time, we'll also be writing our technical report and developing our checklist and protocols. And then the couple of weeks before the competition, we'll be working on assembly and practicing some dry runs of that. Here's a view of the tasks that we expect to complete during these milestones. So right now, the immediate steps after are going to be, again, reviewing the feedback and adjusting accordingly. And we're also going to have a meeting with our mentor where we review feedback from the competition itself, so we can finalize purchases to get those as soon as possible. And then in terms of team logistics, it's going to include finalizing the team roster and deciding on the recovery team to complete team registration, securing housing, all the payment and other things that are due for the competition. And then we will be presenting our flight readiness review with Ezra as well. We'll be doing a lot of testing, especially for avionics and recovery. We'll be testing the descent rates and the coefficient of drag experimentally when we get those parachutes. And we're also going to be making sure that our flight computers are getting good, are communicating with each other effectively and with the recovery system. In terms of manufacturing, most of this is going to be structures. And Matthew or Structures Lee will talk about that later, but we're going to make some adjustments to the bulkhead, attach the rails to the couplers, and work on motor retention, among other things. And the payload is kind of being developed almost simultaneously, but almost separately. We're working on conducting the science and ethics reviews, obtaining the samples, and then making sure protocols for transportation and testing make sense with not only the time that we have, but also the conditions of the competition being in Midland. Here's a summary of our budget. For the rocket itself, we expect a total of $3,700. This is a big chunk of that is propulsion, the motor and the case. We also have airframe, some of the hardware, the flight computers, the batteries, the APRS modules, the parachute shock cords, and a budget for the payload as well. In terms of logistics, what we have detailed here is a plan for the bare minimum for the team to go to competition and an ideal plan where we take as many people as we feel would be the most beneficial for the team, which will include not only sub-team leads that are mission critical, but also new members for them to have some experience as well and set up the team for the next generation of the team with more experience. And that puts us at a total for the project of 6,400 on the lower end and 9,800 on the higher end. At the moment, we have a budget of 4,100, and we have already spent almost half of that on some of the major expenditures. Right now, the funding that we need will be in between 2,300 and 5,700.
So, hi, I'm Leo, and we're with Analysis. And so, one of the primary focuses of Analysis has traditionally been on apogee simulation. And for Phoenix, we have also investigated the flight simulations of past projects to against their performance apogee, and we also investigated any differences between the flight simulations that we looked at. And so, as for some context as to why we put a lot of focus on the apogee, because for this competition there are 1,000 points total, and half of that, or 500 points, come from flight performance alone, and 350 out of that 500 come from the apogee accuracy. And so what you see here, this equation you see, is from IREC, and this is all this is basically saying is that as long as we're within 3,000 or plus or minus 30% of our target, which this year is 10,000 feet. So within 3,000 feet, we can get points. With the maximum amount of points we can get is 350 if we hit 10,000 feet exactly.
This year for Phoenix. The first is Open Rocket and the next is Rocksim Pro. And so here we just have it simulated out on Open Rocket. And up top we have two different apogees here. We have up top an apogee of 9,377 feet, but that's from an error caused by recovery deployment at high speed 33 meters per second. So when we corrected that error, we got the new predicted apogee of 8,930 feet. And so it's a little bit less than 10,000, which is, we want it as close to that as possible, but the stability is 2.33 calibers, and that is within the range of what we want, maybe a little on the higher end. But then we have the Rocksim Pro simulation here, and for this one we have the stability of 2.22, which is a little more in our range that we wanted. And then we have the apogee at 11,889 feet, which is closer to 10,000 than the Open Rocket was. So these are our two simulations that we've got.
Okay, and so what you see here, so these are the graphs produced by each of these flight simulations. So the one on the left is from Rocksim, and the one on the right is from Open Rocket. Those top graphs are the apogee versus time, or the altitude versus time, and the bottom graphs are acceleration versus time. And as you can see, they're quite similar, other than their apogee prediction. And so comparing the two, we were investigating as to why there is quite a big difference between the two. And really the only major difference that we saw between the between Rocksim Pro's and Open Rocket's prediction is that Rocksim Pro predicts the max acceleration to be 8 Gs, while the Open Rocket predicts it to be about 16 Gs. Now, with that being said, it's important to note that these flight sims have an uncertainty of about plus or minus 10%. So it isn't really a matter of just choosing the one that's closer to 10,000 feet. And really what we think is the difference, or the discrepancy between these two, is most likely due to the difference in their software or how they do the calculations. So which one we'll be using? We're gonna use both of them as a weighted average, with a bit more weight given to Rocksim Pro, and that would give us about 10,700 feet for the prediction. And we're giving Rocksim Pro more weight due to its accuracy based on past flight data. So if you see here on the first table on the bottom left, this is Zenith, which flew in 2022. This was a 30K rocket that reached about 21,500 feet, and Rocksim Pro's prediction was 24,500 feet, which was closer compared to Open Rocket's prediction, which was about 28,500 feet. So with that shows how Rocksim was more accurate in that case. But that's not to say that Open Rocket isn't, or doesn't have its use. It can also be accurate on its own, which was the case for Oberon. And for this rocket, it flew and during its 2021 flight, they only used Open Rocket for the prediction, which was about 9,700 feet, and the actual apogee was less than 100 feet away at 9,769 feet. Now, although that's really close, it is important again to remember that they do have an uncertainty of about plus or minus 10%. So this kind of accuracy can't exactly be recreated, especially with a new rocket that we're creating this year. And also Rocksim Pro, according to Randy, we can put more confidence into this one. It's generally regarded as more accurate than Open Rocket. And so we're handing it off now to propulsion.
Everybody, me, I'm one of the new propulsion co-leads. My name is Jacob Eads, along with my colleague here, Wes Howard. Um, as y'all saw, we just got back into it recently. The first things were the goals for propulsion since the PDR. We needed to simulate some possible motor choices for the 10K. Through those simulations, we found that around an L2 impulse was best for this. Anything higher ended up going closer to 20,000 feet. Um, we also looked into those choices with the cost of it. We ended up making a final motor choice through the motors that we looked at. We looked at motors that were available, which ended up only being Aerotech at the time due to manufacturer issues. And then through those, we looked at what was available on sites that we could buy them from, such as Wildman Rocketry. Our last goal, which will be everything after this CDR, will be to learn to assemble the motor casing correctly. We will do multiple dry runs so everybody is familiar with it, and we will make sure whoever will for sure be at IREC is familiar with it as well, not just the propulsion members. Here are some of our requirements that we looked at. We kind of made a soft requirement of a 98 millimeter motor. We were looking at 75 millimeter. Because of our strict timeline, we decided 98 millimeter was better, so we wouldn't have to manufacture any extra pieces to hold a 75 millimeter motor in our 4-inch airframe. We also wanted to minimize the cost while finding the optimal motor for this 10K category. And then once again, stay within that total impulse range of an L2. As you can see on this chart, we have the Aerotech L2500, the Aerotech L400, and the Aerotech M1845, which was outside of the impulse category we're looking at. We decided this impulse category after looking at that motor and seeing that it gave us much higher than our target apogee, and we ended up deciding with the L2500. Let's put it up to what?
So this is the thrust curve for the motor that we selected. As you see here, it's got the dimensions that we wanted for as far as the diameter, so it can fit into the airframe. Don't have to make any adjustments. It's within the class of impulse that we wanted. Max thrust, there was an issue with one of the motors having too low of an initial thrust. So we were worried that it might not even get off the rail with the mass that we had. So we wanted to consider that, obviously. Burn time is listed there at 1.9 seconds, and this is the cost breakdown. As you can see, the motor is one of the most expensive parts of the rocket, but if you want to get off, it's necessary. So yeah, there's the breakdown for the cost there, as you can see. See. Since it is a COTS motor, there's not a lot of things we can mitigate on our end other than just making sure we know how to install it. So that's kind of the main thing we have here. As you can see, here. Assembly of the motor. So if you don't do that right, it's pretty critical to the mission. Probably won't go up. Not good. So if we have videos to show us how to. There's an instruction, pretty good step-by-step instruction video that we found online. So we're just going to follow that step by step during our dry runs. And so I'll start from the left and move right now. So motor assembly taking more time due to new choice. If we do more dry runs, that should not be an issue. So that's why we put that in improbable as well. Incorrect assertion of igniter. Once again, that's part of the video. As long as we do our dry runs and we know how everything goes, then that shouldn't be an issue as well. And that's an issue. And then motor Kato. Now, we put this as improbable because once again, it is COTS. Hopefully, the manufacturer of the motor doesn't, they're not producing anything with any errors. That's what we're putting our faith in, right? Because they're producing these things on a larger scale. So we'd imagine they have a better quality assurance that we don't get a motor that's bad. Obviously, that's a catastrophe. So we put that as far as it can go in terms of destruction to our mission. So, and that's us. So that's propulsion.
Oh, I'm Matthew, the structures lead for Space City Rocketry. Um, Moving forward, in terms of the structures of like the goals we have, there was a lot of change in terms of the scope of the project. We're working, at a different scale. It's gonna be a smaller rocket, still 4-inch diameter, but we're working in a different scope now. So in terms of the goals we had, it was a lot of course, like refurbishing and also integrating some components we're reusing into the new airframe. So, for example, for the recovery, we're going to be replacing the U-bolt, and then we need to prep the new U-bolt, so it needs to be threaded all the way up. Um, Drilling holes in the air, prepping that to integrate with everything else. Screw calculations we've already done. The most important screw calculations on certain items that are going to experience the most load, but that needs to be furthered for every single component that we're going to be doing to reassure ourselves that that's going to be integrated correctly and all work out. Refurbishing couplers and nose cone. There's a couple things that need to be done with that, but that shouldn't take too much issue. That'll probably be some of the things we'll do first. Securing the new fins, and then replacement of avionics bulkhead, but I'll go into that further a little later. In terms of completed, motor retention, we've improved upon that. Ordered the new lower airframe and validated the reusability of components we're going to be reusing. So in terms of the motor retention system, um, it's going to be very similar to how it was done previously, with two nuts on top of an all thread. However, what we are going to be improving upon is using a Nordlock washer. Um, that was something that was recommended to us, and also we also did our own research in terms of like the capabilities of that and how that works. So previously, an issue with the actual motor retainer was just vibrations during launch. Uh, Fasteners tend to walk themselves off, especially nuts and the motor being right below it. So with that being said, trying to actually secure the motor and the motor retainer required you to reach your hand all the way down and then uh, torque down the actual notes themselves, which was only done by a hand ratchet. So in most cases, and like this, you would want to torque down your actual nuts to a specific spec. So we want to improve upon that by using the actual correct tools of something like that, by using a torque wrench with an extender to torque it efficiently to a desired spec so that we won't have that issue as bad, as well as the washer itself that'll help mitigate vibrations as well. Continuing on, the airframe right here that you see on the right was donated to us, uh, as well as the fin can itself by Randy himself. Um, it's a 56-inch, 4-inch diameter airframe. Uh, we're actually going to be using that as the upper airframe versus the lower airframe. So we're going to basically be putting the fins on the new thing that we are going to be purchasing. The reason being is just because for our upper airframe, we're going to be having it 40 inches long, and the lower airframe is going to be 28 inches long. And it wouldn't make sense to cut down a 56-inch airframe down all the way to 28 inches versus us purchasing another 30-inch fiberglass airframe for the lower. In terms of cost and shipping costs of a 30 versus 60-inch airframe, it made more sense to just go about that. And then in terms of reuse components, we're going to be using the nose cone, the avionics coupler, payload coupler, recovery bay, bulkheads, just coupler, bulkheads, and then the motor retainer as well. In terms of the fin and the fin can, they're going to be aluminum. Those were the ones that were given to us by Randy himself. There's some dimensions right there, as well as an image that shows like the dimensions. Up top is us moving the actual fins forward. So in terms of design, we move the fins themselves about 4 inches from the aft of the rocket to better the actual center of pressure, which will give us a better stability for the actual launch itself. Um, and then if we need to, we can always make adjustments beforehand before finally securing it and deciding on the placement of that. But Randy's design in terms of the fins actually helps out a lot, where it allowed us to make that decision on our own. As for the fin flutter analysis, we redid that with the actual new properties of the fins, accounting for them being aluminum, and then the new velocity and such with the actual new launch parameters. It falls within, in terms of fin flutter, 2.15 factor of safety, so that's well within what we would expect for something like this, and you know we don't expect any issues, and there shouldn't be any issues at all with that. As for the reuse of components, it definitely drives down the cost of repurchasing components while allowing us to focus on what needs to be done essentially, which is manufacturing of the things that are going to change. Um, I guess it's what's not broken, don't fix it. Especially with our change of time and accelerated um timeline, we want to focus on doing the things that we're going to do right, which is refurbishing and then manufacturing the things that we're going to be doing new this semester. So in terms of the nose cone, there's no visible delamination or fragmentation of the fiberglass composite structure. Um, Whenever researching in terms of like the viability of looking at components like fiberglass composite components, a lot of the methods were just visual inspection, basically delamination, fragmenting, cracking, or anything of the composite structure itself. So that's what we looked at, as well as the nose cone doesn't take too much load besides it being more aerodynamic. And for refurbishing, we'll be resurfacing and repainting it to prepare it for the new rocket. As for the couplers and the bulkheads, we visually inspected the bulkheads. There is one of the bulkheads for the lower avionics that we are going to be remanufacturing because not all the holes line up properly. Just an error of manufacturing and just in general. So we'll be remaking that to accommodate for the coupler itself. The only delamination we did actually see was on the actual the coupler. You can see on the bottom right, there's that little brighter spot on the top center. There's only slight, like a small circle of delamination. However, the axis that delamination is on is not where any of the load will be placed upon. And if we do later determine that have time, we um, are considering just completely remaking the coupler itself, but we don't anticipate any issues with it. The axis of the screws that the forces are going to be placed upon don't actually affect that area it's at. We will need to reattach the rails to the actual coupler itself, but that's as simple as just reepoxying and lining them up just properly. In terms of the screw calculations, the main ones we've done so far are the payload bay and the motor retainer, because those are the ones that are the heaviest, and during the snatch force and in case of impact under drogue, those will be experiencing the highest forces um, on their actual screws whenever they experience those. So this picture of the calculations, that's basically the Excel sheet that we do use calculations. So that's just an example with I believe this is with the payload coupler, so which is going to be the one of the heavier components with all the experimental pieces within it. So as you can see, we are using 6 screws on top, 6 screws on the bottom, and with a factor of safety of 2.5, the minimum number of screws is 6, so we're well within that range of the factor of safety, and there won't be any issues with that at all. In terms of the motor retainer, the minimum screws was one, but obviously we can't just put one screw. So with it being four screws, we're well within the factor of safety for that structure as well. In terms of the risk, it's a lot of the same that we discussed previously. Obviously, we are going to be doing it at a different scope, so we don't have the worry of, the larger motor and, the higher impulse. So it's actually a lot safer in terms of the structure of the rocket. Um, in terms of fin flutter, it's minimal. We did all the calculations with all the new fin structure and everything like that, and we determined that it's all safe and sound by the analysis. In terms of motor retention, we improved upon the retention method a lot. We thought about it a lot, and with the effective torquing and the locking washers, we don't anticipate any issue with the nuts themselves walking themselves off. In terms of fastener failure, that was another thing we also looked at. Going back to the actual screw analysis, that's where we were going back and making sure the fasteners themselves were up to spec in terms of the forces that were being experienced by the structure, and we were well within our safety factor on that as well. And this is kind of a breakdown on the budget because we're reusing a lot of components and we're also donated components by Randy himself. The cost of the structure itself is a lot lower than if we were purchasing everything brand new. In terms of practice assembly, and we did a practice assembly of all of Shasta's internal components. That was done with the help of Brandon and Izzy. So they kind of walked us through the whole putting together of the rocket from start to finish in terms of the bays, the nose cone, the actual motor and everything, just where everything should fit within the rocket, as well as, just that procedure of going through it. So that definitely helped us a lot of being able to visualize it and, get hands-on, uh, especially whenever it comes to us doing it ourselves and our new rocket as well. And then passing it off to avionics.
Hello, we are the avionics team. Just to quickly introduce yourself, my name is Jake Rodriguez. I am a second year computer engineering major. So to quickly go into it, avionics goals was given to us after PDR or during PDR was to validate both the COTS flight computers, so the telemetrum and the Izzy Mini, adding a fourth stack to the SRED flight computer, remaking the avionics bay tray to fit the four stack configuration, remaking the ground station housing to fit everything into one singular box, adding APRS to the system, developing and fixing both the ground station and the SRED flight computer software, and acquiring our hand license for the ones who are going into competition.
So our main flight computer is the telemetrum. It's our main flight computer. It has onboard live data logging. It's capable of dual deployment. It has an onboard accelerometer, barometer, and GPS. It communicates on a 70 centimeter ham band for telemetry, which requires a ham technician level license. And our secondary flight computer is the Easy Mini. It is capable of dual deployment and only has an onboard barometer. So it is not capable of live telemetry, but it is capable of live data log. Uh, it's our backup in the event the primary flight computer fails to ignite the recovery charges.
Ham radio antenna setup. We use a COT Yagi antenna, which is for the telemetrum. It runs at 433 megahertz and on the 70 centimeter band. For the S-RAD Yagi antenna, that connects to the XB Pro radio, which is the one that's on the SRAD flight computer. It runs on 915 megahertz at 33 centimeter bands. And then we're using an APRS uh, dipole antenna, which is um, it runs on 144 megahertz on 2 meter bands, and it has built in to track. And then there's a ham radio tower at Midland that we are hoping to contact with. It's its own independent system.
So because of our revised flight computer configuration, added an extra PCB stack, and that added a bit of height to the system. So some of the screw holes no longer lined up. So we had to remake the the avionics tray to cut off a bit of height and realign the screw tray switches to make sure they align with our coupler, which we're reusing. And you can see there, we test fit them and it worked well.
Like I said before, we're trying to fit everything into one box. That includes a Raspberry Pi 4, the receiving XB, so the Yagi antenna is actually connected to an XB on inside the casing as well. There's going to be a 3x4 matrix keypad on it. It will have an APR system. It will also have a Raspberry Pi UPS, so we can power the Raspberry Pi through a LiPo battery inside the case. We will probably be making this out of PLA Plus or PETG. The reasons that I found were PLA Plus is very strong and easy to use in the printer, and PETG is also strong, but also a lot more has a higher temperature resistance. But as I'm still prototyping the case itself. I'm open to different filament options. To show you what this is going to end up looking like, the CAD file down there is what the final design is going to end up looking like. It's basically the main screen and the keypad right next to it. This is actually the full wiring structure. The only thing that's different is that there's going to be an extra keypad, but that's just going to go into one of the USB ports on the Raspberry Pi. So basically everything you see here is going to go into that case. To kind of how small this is how small the case will be. Just the extra thing is going to be the keypad going off. It's not very big. So to talk about the risk, we found a lot of our risk were kind of human error in terms of like, just, proper procedures. So in terms of what we're kind of not in control with, it really is improper operation of the SRAD or COTS flight computers causing a misfire or loss of telemetry. What that means is basically software bugs and the loaded onto the flight computers. Loaded as in the SRAD flight computer itself might be loaded with wrong software, losing telemetry. In regards to the COTS, it could be just getting it from the factory and just not being properly configured. The potential is high. The risk we put is high. The potential misfire could injure a team member or cause a delay in launch, and then loss of telemetry makes it recovery operations much more difficult. The way we mitigate this is procedures and testing. We create and look over a pre-flight checklist to ensure safety during integration and testing it along with continuous testing of the system. So just even though we test it first, we validate it, we just continue testing it over and over. If we do that, we do say the mitigation is low. In regards to just to mention lipo safety, because that was mentioned last PDR, we don't currently have them inside two different lipo bags. And these are very small. These are one cell 3.7 lipo battery, so the risk of actual misuse is pretty low. But keeping them in that bag will keep the safety up.
At a total of about $700. We've received our 3 LiPo batteries for the flight computers and for all 3 flight computers, and we've received 2 APRS modules. We are still working on acquiring a second telemetrum, which was brought up during the PDR as being unreliable. And we're still working on getting a Arduino Nano and the keypad for the ground station.
Testing, testing, thing,
Yeah, we can hear you now.
thing, microphone. Closer. Swapped mains and seconded using the tender descenders from Schaff. two-part system where you have a little black powder charge. Everything gets held together in a little clip. It holds the side.
A little bit away, apparently it's cutting. Sorry to interrupt.
The boom tube. The recovery does have some explosive elements to it, namely to separate the nose cone, nylon bolts, the shear pins, they're known as. So at apogee, the telemetrum, which avionics described for us, will send a signal to a 25-gram CO2 primary charge called the Raptor. That will puncture the CO2 can, filling that bay with CO2 gas, and that pressure is enough to break those shear pins, ejecting the nose cone off into oblivion. A few seconds later, our redundant Easy Mini will send another charge, which, if the CO2 system should fail, the black powder system will safely. We've tested this with the existing systems we have to ensure that our black powder calculations are accurate. We'll talk about that a little more in a bit. We're I don't know how. Maybe I'm peaking the light.
By the way, we are in the basement.
Automatically adjust micro zoom background noise removal. Okay, how do we sound now? Testing, testing. Good. Good. Okay. For a few seconds after apogee, I believe we've set it to 3 seconds, 2 seconds. It's adjustable. A few seconds after apogee, the Easy Mini sends a signal to the black powder charge, which blows the nose cone off in the event of a CO2 failure. We're also reusing the firing bulkhead, where it has the U-bolt and the primary bulkhead on which the Raptor and black powder assemblies will sit at the very bottom of the recovery bay. We have a big picture showing the whole recovery system on a later slide. Components, basically everything we don't want to catch on fire, namely the parachutes, but a couple other things, the tender descenders, the drogues, the shock cords, those things will be wrapped in Nomex. We have a couple of different fire blankets. Those will be utilized to make sure that the black powder charge doesn't actually damage anything. Do the thing. Give me a click. There we go.
So right now, we've chosen to purchase new parachutes for the Phoenix. This is mainly due to Shasta's drogue and main not being suitable for our new recovery bay. Like John mentioned, it reduced in size, and also because our Shasta's drogue and main would slow down our descent rate too much, because again, our rocket decreased in size and weight. So we base our required descent rates from the given descent rates from IREC, and we use RockSim as our intended descent rate calculator, but we also cross-reference with other calculators as well, which I'll mention in our next upcoming slides. And yeah, so we just calculate different descent rates for our different parachutes, diameters, and drag coefficients. So here's an example of the descent rate calculations we did. Again, this one's just using RockSim because at the time that was what was most readily available to us. The ones highlighted in yellow are work with the IREC descent rate ranges. For our main chute, the IREC descent rate range was below 36 feet per second, and for the drogue, it was between 65 feet per second and 131 feet per second. And again, the yellow would work. As you can see, for our main chute, we opted for one that would decrease the descent rate the most, aka the 6 feet diameter one. And for our drogue, we opted for the smaller 24-inch because that would
be our best stabilizer compared to the others. So again, drogue for stabilization's sake, and also because the drogue has a really small coefficient of drag, which I'll explain later, and the main for slowing down descent rate completely. So here's where I kind of cross-reference with other calculators. The RockSim was the one I showed you guys in the previous slide, and the RockSim Pro Shastas calculator were also used cross-referencing the descent rates which we got. And here what I did was I was able to calculate the main snatch force using all these simulations in the calculators. And the last one is just an extra calculation adjusting to the parachute weight addition, which we figured out afterwards. So here, from our predicted descent rates, we got the largest snatch force for the main to be approximately 280 lbf, and for our drogue to be 51.37 lbf. And all connecting components have been selected to resist the largest force that they will experience, that we'll explain later in the next slides. So for our drogue, as you guys can see, we changed it. It's not only like a completely new parachute, it is a completely new parachute in the sense that it's a new design as well. It's known as an Explorer drogue, and compared to our old drogue, this is going to expand to form a canopy-like nature. I think it's like specifically called a balloon, but like that doesn't matter. The main reason we chose this was because it has a smaller drag coefficient, as you guys can tell, of 0.8. This makes it really, really good for stabilization's sake. And it's also tangle-free due to the fact that all the shroud is what attaches to the rest of our recovery system, so it won't tangle. And there's like prevent inversion of the parachute as well. And 24 inches, prioritizing stability, and it will decrease descent rate as well, but just not as much as a regular elliptical drogue would. Again, prioritizing stability, and the drogue will deploy at apogee. So these are the material benefits of our drogue. So the parachute itself, its main material is silicon-coated nylon. The main thing I have here is it's water oil resistant. It's an ideal strength to weight ratio and elasticity. I don't have a lot of numbers for this one solely because it is a material we've used before. It's a material we're used to. It's reliable. We're sure of its reliability. The main things I was really concerned about was like the nylon tape and the surge seams, which were present at the connections between like the actual parachute and the shroud lines. So the nylon tape itself has a rating of 120 pounds. The way I got this rating was the fact that I just went with the safest option, which was 120 pounds, which was rated for our parachute use. And if you guys can see here, I did just a regular calculation using the largest snatch force from our drogue calculations. I divided by 6, representing the 6 nylon thread components, which means that each nylon thread should be able to withstand 8.6 pounds. And obviously it can with 120 pounds. So the canopy and mesh are then joined using these seams, and the tape attached with it uses a lock stitch kind of stitching. And then at the skirt, which is a point where all the shroud lines meet right here, there are 28 reinforced stitches. And I assumed, based off of regular parachute ratings, that nylon thread was used. I went with a conservative lower end, which was a T45, in which one stitch would be able to withstand 7 pounds of force. So 28 stitches totally would be able to withstand 196 pounds of force. So this connection here would be able to withstand 196 pounds of force at the junction. So then our main parachute. So our main parachute, we've selected a 6-foot Strato Explorer elliptical, which was our original. We just shrunk it down inside. It went from 7 foot to 6 foot now. It has a drag coefficient of 1.6, which we're already used to. We already know the behaviorisms of this parachute. But the only difference here is we went to the higher end of the spectrum in size to account for the drogue only being used for stability's sake. It should bring our descent rate down to around 26 feet per second, give or take a few feet. And the main will deploy 1,000 feet, will deploy at 1,000 feet when it gets triggered by a telemetrum to minimize drift completely. And another reason why we chose the drogue we chose was because since it stabilizes, it focuses more on stabilizing rather than slowing down the descent rate, it will minimize drag. I mean, it will minimize drift as best as possible as well. Forgot to mention that, but I did just now, so it's fine. Mhm. So yeah, we're not gonna jump properties and like do some illegal stuff. So yeah. So yeah, and then for our main parachute, these are just some calculations of the material strength. So given from our manufacturer, the rating for the shroud line itself is an ultra high polyethylene. So its rating is, it's also known as a spectra as well. Its rating is 200 denier, and denier is like a unit of thickness for a fiber. Basically, what this means is that it has a breaking strength of 17.9 pounds for one single fiber. All the fibers are braided together, and that 200-pound rating makes it so that that whole braid itself can withstand 200 pounds. And so, as you can see from our parachute, we have 12 shroud lines. So, dividing that maximum force that it should be, the main should be able to withstand by 12, for accounting for the 12 shroud lines. Each shroud line itself should be able to withstand 23.37 pound lbf, and easily it can because of the 200 pounds each shroud line can take into account. So another material advantage is the canopy. It's a PAC 7020, which is just a ripstop nylon. It's weighed, woven, and tested according to military standards, which I mentioned in the appendix. I just attached like a link to the military standards used in the appendix. And the material, or like the fabric used, is a reinforced grid-like structure that can stop wear and tear, known as a ripstop weave. And then lastly, between any point where the parachute is going to experience a large amount of temperature and tensile strength, we use a fiber known as Technora, which is a high temp resistant aramid fiber. Most of like the calculations I use for this fiber are in comparison to Kevlar because we're used to using Kevlar. So it's just used at junction points, connection points where there's a lot of heat and tensions. And the good thing about Technora is that it retains 52% of its strength after repeated high stress flexing compared to Kevlar's only 36% usage.
As well as the shock. It's the shock cords from Shasta, the Kevlar strands that actually connect the different components of the recovery system together, those are all still in excellent condition. They're not dirty, but they're not frayed, they're not damaged, so we have elected to reuse those because Kevlar is incredibly expensive when you're buying these half-inch and quarter-inch shock cords. So we just decided save the money, save the hassle, reuse them. Here you can see this is the full recovery system all in one sort of pictograph. This is the lower recovery bay. That's what's going to the front side of that lower assembly there. We have a U-bolt around which everything will be attached. I have a picture of it in a later slide. 1,760-pound quick link will connect. Here, this You know what? We're gonna do it like this. Where's my laser pointer? Do I have? We'll just use the mouse. So, the tender descenders here connect to these two 2,400-pound Kevlar loops, each about 3 feet long. They are threaded through each other and through this 300-pound forged ring. This creates redundancy, so no matter which tender descender blows, whether it's one or both, the main chute will release. So even if we do have a failure, either with the telemetrum or with one of the tender descenders, we will still allow the main parachute to deploy. Until that point, you can see the tension from the drogue will travel down this cable to the forged ring, to the tender descenders, to the bay. When it comes time to deploy the main, these separate, allowing the tension to transfer to the main bag. The drogue chute will then pull the main bag out, pulling the main chute out, connected by this 1760 quick link and 1,500-pound swivel. Still well in excess of the 250, let's just round it to a healthy 300 pounds. We are still well in excess of those loads. After that, the main chute takes over, lowers it down to the ground nice and safely. Do we have any questions on this system? Do questions later.
I promise. We have like 6 slides of risks. They're not all here. You're welcome. There's only 2 right now. So I'm just gonna read through a few of them. The first, one of the risks is harmful BP residue. This could be this could happen due to incomplete burning of the black powder, which is less likely due to the fact that it's just 10K, but still likely as well. Basically, the higher the altitude, the more likely for the black powder to not burn. But yeah. And then, so this can be mitigated from proper BP measurement, packing, as well as testing, ensuring that all the components using BP or black powder are covered by fire blankets, inspection of the components post-flight, and for unburned black powder, as well as cleaning thoroughly any excess with water. And then another hazard we've predicted is burn damage to parachutes. So this can occur due to the improper covering of both the black powder system as well as the recovery system, such as the main parachutes or drogue parachutes, by fire blankets. So this can be mitigated by confirming that our black powder ejection system, as well as our main parachute and our drogue parachutes, are covered completely with the fire blankets. And yeah. 2 more. Premature ejection of the tender descenders, or premature ejection or tender descenders misfire. So this can occur due to improper wiring of the E-match to our terminal block. Our main mitigation effort for this is to confirm that the E-match is secured to the terminal block with no current going to the ground, and making sure that the E-match wires are crossed prior to use, and the assembling of the tender descenders with ejection charges in a safe open area away from any large crowds or bystanders. So yeah. And then the final, for now, hazard is complete ejection failure, where both the CO2 as well as black powder ejection systems fail. This can be caused due to improper E-match wiring to the terminal block, faulty contact between our E-match and our black powder, or faulty contact between our E-match and our Raptor CO2 system. The main mitigations for this kind of hazard is to confirm that the connections with both the CO2 as well as black powder mechanisms are proper before our actual flight, and before testing as well. And then making sure that proper calculations are made regarding our CO2 as well as our black powder testings prior to testing and prior to flight. So yeah, the rest of the slides, like the risk matrix, are in our appendix too, so you can just check that if you want. Yeah.
Obviously, this we did briefly discuss the budget. We do have to spend money to purchase things. So we did decide to purchase a new drogue and a new main at $40 and $250 respectively. We also required replenishment of our shear pins. We used all of our remaining ones at ground testing, which we'll discuss a little bit further on. So we did decide to get a new pack of those at $6 for 100 of them. We should be set for probably a few years. Where we are at now for recovery as a whole, once the new parachutes arrive, they have been ordered. Once they arrive, we're going to conduct some drop testing, whether it's off of the garage or off of a scissor lift. The actual mechanisms for the ground testing we are still finalizing. We're also trying to do a collaboration with a local fire department, perhaps one of their ladder trucks. Gotten a little bit of pushback on that, saying they're for emergencies only or something, but regardless, we will test the parachutes before we actually use them. We are also waiting on the new upper assembly, the actual front bit of the rocket where we're going to put our bulkhead. Once that arrives, we're going to conduct a second series of ground tests to make sure that our black powder and CO2 calculations are good, as well as the verification of the new telemetrum, which should hopefully come in sometime soon, just to make sure that everything is working correctly. We also have already conducted some testing, both with us and with avionics. On March 7th at Hamfest, we conducted ground testing of the complete ejection apparatus as it is now. We placed it in the old Shasta upper assembly and adjusted our calculations for that increased volume. The CO2 system functioned nominally. Everything worked as expected. The black powder system was slightly overtuned. On review after the fact, we found that the calculations for Shasta were done with a 10-inch bay, which is slightly shorter than the actual size of the bay. However, we included a 20% safety margin in our calculations. We measured that it would require 1.64 grams of black powder. We reduced that to 1.3 to ensure that we didn't just detonate the thing. As you will be able to see in the video, nothing was damaged. The test went as expected. It was just a little more peppy. Here you can see a video showing the full assembly. This here is a black powder charge packed into a tube with some wadding. This is the smaller Raptor assembly. And then, as you can see here, is the full assembly with the full-sized Raptor and the black powder detonation tube. Here's a video of the actual black powder system. Or sorry, this is CO2? We had a couple of failures early on, so I was very excited it worked. So yeah, sorry, I mixed up my headlines. That was CO2, this is black powder. A little overtuned. However, because we did secure the nose cone with the Kevlar retention strap and made sure that we were in a nice open field, nothing was damaged, we didn't shoot the nose cone into the side of somebody's house or anything like that. So everything went as expected. We have also conducted some battery drain.
So on March 19th, we completed a set of battery drain tests using 4 lithium polymer batteries rated at 3.7 volts. These were the old batteries, not like the new batteries they just got. So by setting our added value to our max voltage battery, so here it was just the Y-intercept, we set that to an ideal 4.2 volts, assuming like the batteries were fully charged, and then we calculated essentially how long it would take for each one to reach a minimum voltage of around 3.2 volts. This is not ideal. Ideally, it would be 3 volts, but again, we can't always have what we want. It's 3.2 because putting it down to 3 would just be ludicrous. So each battery was calculated to have ideal conditions of about 2 amp hours of capacity, with our battery B draining the slowest, and our battery D draining the fastest. So, but all of them totally were rated for usage, for like well usage. These are just some pictures of the system. It was a 2-hour process. Be thankful I didn't put a video in. We made it a series circuit. You guys can't really tell, but basically we connected a resistor in series with our batteries here, as you can see, and then connected it to the ammeter and just took some probes, again, measuring the voltage decline of the battery after 5 minutes. Okay. In like few minute intervals. I think 5-minute intervals, yeah. And then this was our initial voltage, and our final voltage was 3.6 to 3.8. Again, we didn't go all the way down to 3.2, but we assumed we kind of just calculated based off of the data we have how long the batteries would be able to go.
Did do validation of pressure temperature testing. This was the purpose of this was, like I said before, to validate both the telemetrum and the Easy Mini flight computers are functional. As I was going to show you videos in a second, both performing as expected and deployed both at the apogee and at the main altitude deployment in the pressure chamber. Both flight computer systems seem functional based on this test, with the telemetry working during the ground test as well. However, based off feedback during PDR and out of caution, a decision has been made to purchase a new telemetrum, and that will be revalidated once that has come in. To show you kind of the Easy Mini deployments. So the drill goes off, and this one should be the main. So, and then don't do that. There we go.
So Jake said we tested both COTS flight computers in the pressure chamber, and here you can kind of see the live data we recorded off it. Basically graphs the height, simulated height, the speed, acceleration over time. Yeah, there's not much else to add about that. Thank you.
Hi, so for payload, our goals are to design an experiment to study the effects of low hypergravity on sea urchin sperm, and also to have a structure that's capable of withstanding a requirement such as temperature for the experiment. So some of the major updates that we have is our target temperature. So rather than trying to keep the samples at -80 degrees Celsius, we've shifted it to 4 degrees Celsius, which has been very helpful. We've also finalized our sample acquisition, and we have contacted IACUC, which is the ethics board when we're using animals, and they said that we don't need to have any certifications or anything for sea urchin testing because they're invertebrates. So a little bit of a recap on the background. So since we are moving into a new age of space exploration, we thought it was very important to study the effects of stressors surrounding launch on gametes, and so we have chosen this avenue of biomedical research aboard the rocket, and so in the future, when they start doing this, they'll most likely be using gametes as it'd be more efficient than live animals, and we've chosen to use sea urchin sperm because of the similarities that it has to human reproduction, given that they're used as development models for humans. Okay, so our hypothesis for this experiment is that we hypothesize that as a result of the low hypergravity associated at launch, we will see an overall decrease in sperm health. So this could either be through the 3 metrics of sperm health that we had mentioned at the PDR, which would be we'd see a decreased overall count of sperm, or we'd see more clumping of the sperm or morphological changes. Also, since we are no longer cryopreserving the sperm, there might be more damage as it would be fresh sample. So we still plan to use sea urchins. I think the next slide, yeah, is our decision matrix regarding that. So looking at the upkeep, the accessibility, viability, and ethical concerns, we found that sea urchins would be the best model organism. And so we're either going to be using pencil urchin or green sea urchin. We're kind of leaning more towards green sea urchin right now, as that is the one that is available in the embryology embryology kit that we were looking into. So the kit that we finalized, it has the urchins, it has everything we need for sperm extraction and for sea urchin survival. And yeah, due to us not finding any labs that were willing to donate sea urchins, we found a kit that has everything that we need. So this is the updated protocol. So we no longer have the cryo and thawing protocol because we won't be doing that. Our protocol for analyzing sperm health before and after launch is the same, and that's in the appendix. An update to the protocol is how we're harvesting the gametes from the sea urchin. So we will be injecting some potassium chloride into the urchins. We're approximating 14 sea urchins, 7 of which will be male. We're trying to look into requesting more males, of which they're saying 50% would be fertile. So we're expecting 3 or 4 fertile male sea urchins. 1 sea urchin is all we need per trial, and it will produce around 3 to 4 milliliters of sperm. And so we would inject the urchin with a little bit of potassium chloride, and then shake the sea urchin, and then place it mouth side down in a petri dish for 1 to 2 minutes, let it rest a little, and then the sperm should just appear up. I think we have a graphic around the top of the urchin, and you would just extract it with a pipette and the syringe. And then this sperm is considered inactivated because it hasn't touched the seawater. So inactivated sperm can actually survive on ice from between 2 to 5 days. And there have been studies that we've seen where they've survived for 12 to 20 days, which is a longer range, but 2 to 5 days for sure. And then all the harvesting methods are from UW's, University of Washington's Sea Urchin Embryology Core Lab. And then here's some graphics on how the injection angle works. And then so some of the future testing we have prepared is sample preparation. So we would need to practice the extraction prior to the actual launch. And so working on our pipetting and syringe techniques, focusing on minimizing the sample loss, and then also storing the urchins. As of now, the kit that we're planning on ordering has seawater in it, and sea urchin storage is straightforward. It just needs to be in the water at room temperature, and we would need to measure the pH of the water, which needs to be between 7.7 and 8.5. Measure it every week, and then feed the sea urchins bi-weekly and shift out the seawater every 3 weeks. So it was a pretty straightforward upkeep of the urchins. And then also we're planning centrifuge testing to test speeds and durations to determine the optimal conditions for sperm viability, and also collect data for insight and trials. Right now, we're still working with analysis to figure out the conditions of the centrifuge, but right now I believe it was like 309 RPM is what we're thinking. So the biggest change I'd say is our shift in temperature going to 4 degrees from -80. The reason this is beneficial is one, our sample can survive at that temperature. Previously, we had considered mouse sperm, and so that needs to be kept at -80, but sea urchin, it can be kept at 4 and be fine. And so it's just a simpler infrastructure, so like it would reduce the logistical challenges significantly. Also, there would be a reduced risk of sample damage prior to flight. So, cryopreservation and thawing, you lose you lose a lot of sperm doing that process. So, this would reduce that risk. And then also, sperm stored at 4%, 4 degrees Celsius remains viable beyond the required testing window. So, it would work with what we need, the time frame that we have. And then also we have more readily available equipment for the 4 degrees Celsius. For example, like thermometers that we already have present at the lab. So this would just be overall more beneficial. And then this is the risk assessment. So some of the higher risks we have is like regarding temperature. So the first one is poor insulation, could cause temperature fluctuations and stuff. So that would be pretty bad because the sperm viability is dependent on the temperature being at 4 degrees. Although that is a big step up from -80, it still needs to be kept cold. So we're working on the design to mitigate that risk. So monitoring temperature and then minimizing the time outside. Also, sample contamination is a risk. It's not very high because it's not very high, but we will take extra care in using sterile techniques and performing all the things that need to be done in a proper way. And we're planning on practicing with the centrifuge test, so that should be mitigated. Also, rocket-induced stress, like vibrations and accelerations. So these mechanical forces could impact like vials. However, we're looking into securing the vials properly and also researching vials that are less likely to leak or break. We have the cryo vials that we had researched last time. However, we're looking for perhaps a cheaper alternative since we don't need to go so low in temperature wise. And then sample handling delays, so delays in like retrieving the rocket could be harmful as the sample does need to be kept cold, but we're planning on doing the analysis immediately post-flight and not like taking it anywhere, so immediately on site would be helpful.
Isn't where we want it to be currently, but previously with previous scope of negative 80 Celsius for roughly 12 hours, we were looking into keeping what's pictured here, and what I have physically a pressurized vessel with dry ice. With the lower range, with the warmer temperature range that we have now, not being able to go below -5 Celsius, but being able to go up to 15 Celsius, that's roughly 8 to 52. This opens up a lot of options. And there are a lot of options with this structure going forward that we can narrow down our options very quickly with testing. Testing for I joked that, well, how do I know that it's cold in there? Okay, well, let's feel that outside negativity. With this, with the new scope, water is a decent test, and there are Bluetooth temperatures. Uh, this design will be finalized before manufacturing because uh, previously a lot of engineers have solved this problem. Uh, so uh, this is the part we've been warned about, I should say. Um, so we're working with what's a good solution to this. Uh, Here in this picture, we have the aluminum, sorry, stainless steel 304 thermos. We have a phenolic liner that is used for protecting motors when you make your own motor grains. And we have an aluminum casing, and pictured down here was previously used sort of as ballast to add weight to the market. It's something very unique about the payload coupler is that on one end is the center of gravity, and on the other end is the center of pressure. So depending on how we play with the placement of all this, we can fix any problems arising with stability. But this is an open problem. and y'all's feedback would be readily received.
So the budget that we have right now includes the sea urchin embryology kit. So this comes with all the syringes, vials, the urchins themselves, seawater, potassium chloride, everything that we need for processing. And then we also have this dye. It's needed for assessing sperm health, and there's more information in the appendix about that dye. And then we also have a microscope on here. Just in case, if budget allows, basically. But we're also looking into contacting Texas Tech and seeing if we could drive up to any professor's laboratory and use their microscope. So we're still working on that. But we believe that if we have the budget, a microscope would be a pretty good investment, not only for this year, but for the rest of payload.
Understand that with the time frame, there is it should be considered that we may have to fly ballast or we may have to repurpose old cooling systems. So not to say we don't have faith in ourselves, but we're just to be realistic. We understand the pressure that we're under.
Well, now that you've seen what all the subsystems have been working on, a little bit of insight into what comes next for us, at least immediately. We will be taking in all the feedback that we get from today and integrating it as needed. We'll have meetings with our mentors, including our flyer record, and also take into consideration the feedback from our safety reviewer assigned by the competition. And this is also going to lead us into finalizing all the logistics about everybody that's going to competition, finalizing the team roster, and dealing with housing. We will also be doing all the testing that's needed, primarily in terms of avionics, payload, and recovery, and also working on manufacturing as soon as we get those items that we have purchased or are in the process of purchasing, and also dealing with any pending repairs in terms of the internal components. So I want to especially definitely thank all of you that are here. It has meant a lot, but also this is a list of the people that have, I feel, helped a lot to our sub teams directly. Some of you are here. Thank you to everybody also that is online and everybody that's watching this video after. Special thanks to Randy, our flyer record. Some of the mentors that we've worked directly with are Brandon, Izzy, Alex, Christian, Javier, Kelly, Eric, Robbie, Gustavo, Haley, Irvin, Emily, Christian, Samar, Raj, and Jalissa. Okay, I guess testing again. I don't know what could be John's not even talking, so I don't know. This says, I mean, when I speak, it's lighting up the microphone, so I don't think it's okay. I don't know how to move this. Okay.
Then waiting online.
Okay, sounds good now.
By the way, they're in that chat on the list that we have, and some of them have been answered. So, yes.
Okay, do you want to show us the list, or are we going through? Maybe we.
We can show you the list later. If anybody
Okay.
wants to raise their hand online, that's great. I don't know if they can hear me.
Yeah, if anybody wants to raise their hand, we can take questions that way.
Randy says you have to talk directly into the mic, by the way. Yeah.
Okay, if I talk directly into the mic.
Y'all sound good right now. Like, you're fine.
Okay, thank you.
Yes, now y'all are fine, but if your head is turned sideways, the mic is picking it up as noise and canceling it out. That's why whenever the speaker is facing any other way than the mic, you don't hear them.
Yeah, like we can tell y'all are talking. Like we see you're like motioning, but it's just quiet on the line.
Yeah, noise canceling is killing you.
Okay, thank you for letting us know. I'm sorry. So I have a question.
Yes, Randy.
Who made the recommendation to buy a new altimeter, altimeter, and why?
Hi, yeah. So this is Kurt Rowland. I'm one of the avionics leads. It seems like last year the telemetrum cut out halfway through flight. Ended up not sending the telemetry data down to the ground, and the only way to find it was with the SRAD system, which worked flawlessly, by the way. We have some theories on what it could be. I haven't ruled out the antenna that we added, but due to the fact that it only happened in flight, we just didn't feel confident flying this telemetrum again. Therefore, we've bought another one, brand new out of the box with the original OEM antenna, which will actually aid in some fitment issues we were going to be having this year with the shorter bay as well. So,
Okay, so I understand your rationale, and that's reasonable. I just want to remind you that the first time you fly an altimeter is the highest probability of it failing on flight. So unless you've flown this altimeter multiple times, you have no history of it working properly.
okay.
And a second comment I have is when you were evaluating your apogee, altitude, and margins of error on the between Open Rocket Pro, Open Rocket, RockSim Pro, you all are very correct. Both of them are using different algos for determining drag coefficients, and that will affect this altitude that it shows up as. One of the things you have to, y'all, I don't know if you took into consideration or not, but whenever you're looking at the data from the altimeter, there is an error, a published error, and in my last memories, it's at least plus or minus 10%, and it may actually be greater than 10%. The only thing with the smallest on barometric pressure only, so that's the tele-easy or the telemetrum, which isn't using GPS, are going to have the highest error bar. The only thing that has the lowest error is the GPS, and even it has its issues. So those are some things. Plus, whenever the rocket goes supersonic, international codes kick in, and the altimeter stops updating, except once a second. And then once, if you're over Mach, 1 second's a long ways to get an error band.
Yes.
So there's a bunch of other avionics functions that you need to consider, and your SRADs kit is also subject to those. So you really have to do a deep dive into their errors and propagation of errors based on different conditions.
Okay. Yes, that's very fair. And we are aware of the shutting off of the GPS during ascent and descent.
Yeah. Well,
With
descent only if it's only coming down ballistically, and that's not a good thing. So it doesn't matter if it's ballistic, but going up, it does matter. So, but just some things that weren't mentioned in your discussion or your analysis. That's only I bring them up. You may have already considered that. I don't know.
No, that's a fair point. With three separate systems, completely separate systems, we are hoping that we're assuming that we're going to have some better data. If one of them cuts out sooner than the other, then we'll have overlapping data. And hopefully, at least on descent, we'll have more than one beaming back. So
Oh yeah,
we'll be able to compare average and
the GPS tracking. But again, you have three altimeters. They each have their own errors, and so you got to your errors actually go up by three, the factor of three, because you got three different error bands to consider. So if they're all 10%, you effectively got 30% worth of error in your data. It's propagation of error. Go review that.
Sure.
And this is something I have to deal with in my professional life. So when I'm doing advanced process controls in the chemical industry, as propagation of error on all the measurements, it makes a big difference.
Okay, thank you.
Hey, Randy, can you hear me?
Yes, sir.
Awesome. I have a question about what you suggested at the very beginning. What causes the higher likelihood of failure for a brand new flight computer? Like, what's that cause, and how did it go? How did it become more reliable after every flight?
Because you know it works. Right now, you take it out of the box, it works on, and it works under normal gravity, but as soon as it gets hit with 10, 20, 30 Gs, you don't know what's going to happen. It's unproven. Everything they've tested, they go through their test regimen, they know it works, but as soon as you hit it with 30 Gs, you don't know what it's going to do. You may have a component come loose. You may have a bad solder joint. You can do visual inspections. You can do a whole bunch of other stuff, and don't go putting a whole bunch of hot melt glue on it, because you're going to have a heat problem. But and there are other things you could use to other silica non-conductive stuff that you could use to put everything together. But again, you're now modifying the manufacturer's kit, and they haven't tested it with that, so you don't know what the effects are going to be. Until you fly it, you don't know it. And then so in the amateur ranks, we don't really trust altimeters until we've gotten some flights over them. And the description of your problems sounds more like a bad wiring connection to me than some other problem. Although there might be a loose piece of kit on there, and microscopic examination you may show up a cold solder joint that was unforeseen, that held up for a couple of flights but now doesn't. But since you don't know it, you don't know
What
until
examinations?
you test it under G's.
So what examinations can the team do on the previous flight computer to verify that it was a physical problem or not, versus what they decided, which is buying a new flight computer?
Okay, so what you do is you put it into a rocket and fly it, and check it. That's all. It's the only way to get all the data, unless you build a centrifuge and a vibration table to try checking it with. Those are the other things. I mean, that's what the aerospace industry and industry in general does, where you have high vibrations and high G loads. You take rattle and roll it till it breaks.
I'm assuming you need a subscale rocket, right? Not the full kit and caboodle.
So, I'd start to trust it. I always, in my experience, I have flown. When I get a new altimeter, I put it into a rocket and fly it 3 or 4 times just to see if it survives those 3 or 4 flights with known good altimeters. And I use the motor as the backup recovery system. And black powder always works.
Hey, Randy, I'm assuming you mean a subscale smaller rocket, not the team's main vehicle. Is that correct?
No, you don't have to use it, but a small light rocket, so you can with a good fast burning J motor, so you hit it with maybe 40 or 50 Gs would be fine.
Copy.
I mean, so that's what, a nice red or blue or green motor, which we all know burns very fast, would help you, and it's lightweight, so it takes a lot of shock, but that becomes your test vehicles.
Okay. Understood.
But you're out of time. Right? This is April already, so y'all got to get it. Y'all got to figure out how you're going to get there. Make your best choice. You're the engineer of record.
Sure.
But I do want to warn you of possibilities.
I suppose we were weighing the odds between an altimeter that has failed and a brand new one.
But did it work when it got back on the ground?
The data, to my knowledge, was continuous.
No.
So
I didn't ask
was...
about the data. I didn't ask about the data.
Okay.
The question was, when you hooked it back up, did it power up and act like it worked?
Yes.
Bingo. That's why my first assumption is it's a bad connection. Not a hardware problem with the altimeter. That's my clue. Am I making sense?
Yes, sir.
Because if you had a component that came loose, it could start back up, but it's more likely not to because it's been broken. And I've had on my L3 flights, I had my featherweight on-off switch failed. One failed at takeoff, turning off one of my altimeters, and the second one failed right after the drove chute charge failed at apogee, and so the rocket came down on its drove chute, and I still flunked my L3 flight because it wasn't to the flight plan. But the point is, other things can come loose during all that flight, and now hot melt gluing all the wires down so they can't move is number one on my list of how not to have a wiring issue.
Okay.
Number two is all wiring is completed, tested on the ground, and you don't touch any of those screws when you get to go to launch it. The only thing you do is put the battery in, and you make that a robust system.
I want to add to what you said about those connections, because I noticed that some of you guys had faulty contact as one of your causes for risk. And I wanted to ask about what you were doing to mitigate or ensure isolation and proper contact. Like, are there secondary checks? Are you checking the continuity and isolation? Are you looking at all the wires?
Okay. You got to be careful with checking continuity, because if you've got your ejection charges attached, that continuity check might do something you don't want it to do, because you're putting amps on it. Be very, very, very careful with how you're doing continuity checks. That's why I said you build your electronics on the ground, and all you do at site when you're getting ready to fly is you install your batteries, you install your injection charges, you make certain they're safe, and then you install your batteries. No other wires should you be putting together. And remember, every manufacturer has a required torquing value for their terminal blocks. Be aware of those and use a decent torquing screwdriver to tighten them. No Godzilla tightens. You're liable to strip them. And that has been a cause with wires coming loose. Also consider using ferrules on your wires if they're use multi-stranded wires with ferrules because they're less susceptible to breaking in flight. And that was all developed by the aerospace industry. That was a hard lesson for them. So just some things to consider. It's your rocket. Y'all get to do it your way.
Yeah, just on what you guys were doing to ensure the isolation and making sure you guys were that the wiring was safe, but not getting clipped into any pinch points when you're inserting the avionics bay. I'm not a rocket amateur rocket person, so I'm seeing a CDR for the first time. I'm a spacecraft girl, so I don't know all the ins and outs. But I do know what you have to do to make sure that your harnessing is done safely and correctly. So I'm just curious to hear from his side. What's
I'll send you some pictures of my correct rebuilt L3 A bay with everything installed and in place. It may be ugly, but it hasn't failed me. And that's all I'm. So, anyways. Oh yeah, and that was before you could get laser printer or laser printers to cut up the plywood with. It was all done by hand. So, but it works still.
No.
Randy, can you hear us?
Yes, sir.
Okay, I believe that was a question directed towards the rocket team from one of the audience.
Oh, what was the question?
About the wiring continuity.
What about
checks.
it?
It was just a question directed towards us.
Oh, okay. No, I didn't hear the question.
It's okay.
Yeah.
Hmm.
Answer this. Who can answer this?
Yes, like Randy, with you don't want to do continuity testing with the charges attached. However, the other cables, like the telemetrum, to your wiring harness, you can measure continuity there. You can make sure that the wires are secure. You know, when you tighten them into the wiring harness with the tightening screw, you can give it a little tension, make sure that it's not coming out. You can ensure that there is, at the very least, a secured connection, if not, you know, one that you've run a charge through, because if you run a charge through it, it goes boom. There's only so much that you can test without actually setting the system off, so you're pretty much limited to continuity up to the wiring harness and making sure that the E-match wires are secure in the harness. But the we didn't have any faulty cables with Shasta, I don't believe. I believe it was just to the signal transmission from the telemetrum, which, you know, I wasn't on the team for Shasta, so I don't know what perhaps caused that. But
That's what I was wondering, like,
yeah.
if it was something that happened at the connection, like point at where it was meeting, or if it was something further down the line, if it was just, you know, too many.
Jake may be able to answer this. I believe the antenna is on the board. So yes.
Oh, until PDR that the Shasta, like the original telemetrum, didn't work during flight. That was the first time we ever heard about it. And as far as I understand, they never even told us what the failure point was. So they were just kept asking us how to test it, how we were going to test it, but we didn't even know it failed and didn't deliver into telemetry data. Like this was all new to us, and we were trying to figure it out from there. So like that's, you know, and then like we said, we were going to pressure chamber test it, and they said that's not sufficient enough, and then we're like, it was just a lot of like trying to figure out and stuff like that, and so that's kind of it was something that was very big concern that was brought up during PDR.
It's definitely worth asking. That was something that caused such a huge point of failure, and if you can mitigate that for this one, definitely worth it. It'll be the first time you're flying that what's it called? Yeah, the new flight computer. So just to prevent that from happening again, make sure it's flying safe. So it could be there's just so many things that I've noticed that's quite silly in terms of something could have gone wrong so easily. Like just there's too many wires that are loose and pinch points and tools being used incorrectly and the insulation to the wiring getting nicked and then you're causing all kinds of mishaps there accidentally.
I will say like some things that the past members brought up of like the reason why they just thought like it didn't work, and that was because one, apparently they dropped it at some point, like they said like a meter or something, I don't know, and then they said like it had some rough landings and stuff like that. Now from what I understand, it was just telemetry, so we stopped receiving telemetry. The charges actually did go off properly, so it did work as intention, which the main point sure we want telemetry, but we do have redundant systems for that. But at least the actual recovery charges did go off properly and stuff like that. So that was the positive that we learned. So at least the recovery charges work. It was just the telemetry that was non-functional.
One question that was not answered that she asked was how are the actual wires being secured within
the flight computer
avionics bay so that during installation you know that it won't, something will not get pinched, nicked, and be damaged.
That's right. Very small amount of failure points. Dogs are making sure that harness isn't like 3 feet longer than it needs to be. Then you're doing great. That's awesome.
Is there secondary retention on the M10 threaded thing, or is it just pure retention? That could be I say secondary retention. That's super good. I think that's totally fine. Yeah. Yeah. So,
That's actually something I was gonna bring up with your structures thing, but I will let you go real quick.
More questions? Did someone raise their hand online?
And that was Jalissa, but she had to pop off. And also said at 8:30 that we definitely not hop back on. But if y'all just at her later tonight, she can see you her questions and
I have a question. Why test the CP of the parachute? Do we not trust the vendor? What's up with that?
Because of the stability, the only way we would be able to determine the coefficient of drag is through testing. That's the reason why they have it. It's not that we don't trust the vendor, it's just for redundancy purposes. We want to make sure all the calculations are proper. Just in case there is like a small deviation in the coefficient of drag, we want to be as accurate as possible with our calculations. Okay.
So what test will you do to determine that, and how will you ensure that your test is accurate, as accurate? Like you could do your own test, and then you're plus or minus 50%. So then what the hell was the purpose of the test?
So basically, one of the main reasons we do a test is we use a rocket equation which relates the drag force that the rocket experiences, or the weight of the rocket, alongside the velocity with the coefficient of drag and the area, or the reference area, all those terms together. We don't have a marker. I would have written it down, but it's all like proportional in the sense of like the weight of the rocket is going to be equal to all those other terms. So if we don't have one term coefficient of drag, when we do our actual testing, like our parachute testing, we will have our velocity descent rate and every other parameter, the reference area, everything else, the weight of the rocket, everything else, and we'll just have to isolate the coefficient of drag. And then if we get something close to 0.8, great. If we don't, then we know there was a small mistake, and we'll account for that in our future testings and future calculations as well.
The actual
And also, we will be doing multiple testing, like different testing areas. We have different areas we have in mind so far, like certain buildings, basically just different height testings to ensure accuracy. So all those things combined, we will be redoing the drag coefficient calculation.
you know how tall of a building you need to hit terminal velocity at your expected.
I'd like to add something. Brandy's leaving. Okay. Bye, Randy. Thank you.
Goodbye.
We'll talk tomorrow. I just wanted to add that I think the biggest benefit of doing experimental testing with the parachutes is to see if they work as intended. It would be a big problem if we calculate the coefficient of drag and it's something like 0.1 or instead of 0.8 or something like 2. If we are somewhere close where at least we know that the there's no manufacturing issues or there's no major manufacturing issues, as well as the descent rates, that's a more experimental thing. So that's more so the focus of validating with the experimental testing of the parachutes. Not necessarily getting an exact coefficient of drag. For that, maybe we could chop the factors a little bit. Yeah. To that point, yeah. If there was an issue where it was really different, we would probably have to contact the manufacturer and see if they have any other recommendations or if we need to get a replacement. But that's a major goal of those tests. Oh, I forgot.
Other than Randy leaving, Tommy had mentioned regarding the handling of vibrations on hardware, why lock washers over nylock nut? Lock washers are incredibly finicky and can still loosen from shock or vibration. Plus, once they come loose at all, there's no more ground for them. He didn't really ask us, but he just kind of like, yeah. I do have those too. It's almost as big out of mega. Suggested nylock nuts instead of the washers, the lock washers.
Okay, yeah, so that would probably be something we have to look into as well. Whenever originally determining that, that's something I had discussed with some of our mentors, trying to decide on what the best method was. Um, Originally, like I wanted to do like securing with some sort of like aircraft wire the nuts or something like that. But whenever speaking to Randy and some other mentors, they were saying like just the nuts themselves or putting some sort of lock washer would be good. But of course, other options might be on the table as well. For example, nylock nuts. I've used those before in Rocketry for motor retention. Um, but of course, we might just have to do more testing on that as well.
Can I answer that?
Yeah.
The lockouts are great, and here's the you mentioned Loctite not being like up to being able to withstand the correct temperatures. There's definitely ones that take higher temperatures. There's also VC3 and other thread locks that can definitely take that higher um, temperatures. Torque striping with epoxy. Um, there's also those are like there's just a bunch of options that not only are you better safe than sorry, they're all removable too.
Mm-hmm.
The VC3, for example, um, that it's like really sticky. It's kind of like the Loctite. I've never used Loctite myself, but the VC3 is a good one. And just pouring on epoxy, it's not going nowhere. You know, it's not exactly torch striking. There is a right way to do it.
Okay. You're reading that one. Yeah.
Yeah, sorry. Yeah, VC3 you take it off with acetone or something. It's that. Yeah.
Okay.
And then epoxy will take it off. Um, if you're doing it like torch striping, the whole purpose of it is to see if it's moving, right? And another thing I want to ask is to if you knew where the points of failure was for the other nuts that were running away, like did you recognize the like where were the fasteners located?
So for the actual, so on previously on Shasta, they used the same motor retention, which is two nuts stacked on top of each other, and they didn't come off fully, but they did walk themselves off like a decent amount to where they were worried about it, and they advised us to try and come up with better options for keeping them secure. Um, that's why I was trying to look into options, including just torquing them down a lot harder versus just the hand ratchet. Um, but especially because there is not a lot of space, and having to stick your arm down an actual airframe is kind of difficult to be able to secure it. Um, it felt like it was kind of limited on options, but yeah.
Same thing. I agree there as well. And making sure it's serviceable. I understand that your bay is different now, So you showed it to us yesterday. It seems like the situation with the bolts are completely different and hopefully more accessible to you guys.
Yeah.
And making sure it's serviceable is just such a huge thing. If you can't get a torque wrench in there, it's built wrong. Like you're setting yourself up for failure.
Yeah, that's something I wanted to, because I know because the lower airframe is going to be shorter, that we will have a lot easier access. So torque wrench is definitely something I want to incorporate to make sure that, we're actually putting some tension on it.
Yeah.
Should it not just be done outside of the airframe, like torque onto the bulkhead outside?
Well, because the bulkhead is secured with four screws all on the corners, and then it's inside the
Sure,
bay.
like,
So
can't you like assemble it outside and then slide the entire assembly to the airframe? Right, like
True.
here's your motor, here's your bulkhead, connected via thread. You do this on the ground, and you slide the whole thing into the four external screws.
true, that could be done. Yeah.
Yeah, that's okay. And
Sure.
you have full access to the
ones
bulkhead on top, like the single bolt or the single nuts. I mean, no need for special tools or super long ratchets. Usually, right in front of you. Okay, I'm not.
No,
No, yeah, that makes sense. Yeah.
I have the design, so I'm just like, it's how you make the thing. But that would be way easier, especially if you're just aligning the bolts correctly and putting like thread lock, for example, just on that screw that has no nut on the other side. That should be more than enough, but protection and torquing it correctly, obviously.
Okay. Yeah. So for what y'all are saying is probably nylock or some sort of high temperature. Um,
Both.
Okay.
Go. Who cares?
Okay. Okay. Yeah, I'll definitely take that into account and decide that going forward. Of course, um, just changing securing of nuts isn't something that would be a difficult change at all. So that's why I'm also keeping it open to, options of advice of everyone giving me as well.
How about I want to change question topic, okay?
Okay.
How much, how about things for the project manager? Um, how much cost, I say how much cost is people and how many people? Whenever you're talking about the Rocketeer fees, how many people is required? This is a pretty big team. How many people is required? And I know everybody, often everybody does, but it's the um, sad reality that, that's not economically feasible. And that's with any team or company or whatever.
Yes, I can definitely talk more about that. Um, the reason that we have a minimum and an ideal is basically what you're saying. The minimum of what we consider mission critical would be first the chief engineer and project manager, because a lot of the protocols do require the lead and alternate lead of the team to be there. In addition to that, we would need at least one recovery sub-team lead, at least one avionics. Okay, I'm counting. At least one avionics lead that is ham certified. And we would also need our structures lead there. And for the payload to function in the way that they have designed it, for them to do the testing in place, they do need 2 people. So the payload team would make the total 7. And that is our absolute minimum requirement. It would mean that we don't have a propulsion lead there. However, Chief Engineer Alfredo was previously the propulsion lead, so it would mostly be on him to deal with that, and Matthew as well, our structures lead, to deal with motor retention. Obviously, 7 people is still it's very tight. It's pretty much the entire recovery team. The recovery team is about 5 people. The people that can actually go and physically get the rocket back. Okay, I'm gonna actually get to the. So that minimum is for the logistics would mean that 7 people go, and also the reason that the Rocketeer fees is 0 is because it would mean that we are paying for our own Rocketeer fees, which is $75 per person. In the ideal case, we would not have to pay our own Rocketeer fees, and that would include 15 people. So we do currently have 15 leads in the team. Not all of the leads would go, mostly because of availability. But we would also like to include at least 3 non-SCL members. Um, More so new members, maybe more so sophomores that are going to have a better chance at carrying the team for next year and are going to have competition experience that's going to be really beneficial to the team. Because right now, the current team, actually, the only person that has been to competition is Matthew, our structures lead. And that has been a little bit of a limitation. So we would. Oh, I'm sorry. Yes. Okay, we do have 2 people. I'm sorry about that. Yes. So we have 2 people on the team really that have been to competition. Although Matthew did not even go with UH. Um, so let's say one. So we would definitely want to set the team up for success for future generations by sending people that are not just mission critical, but so that they can have the experience and carry the team as well. So that is on the higher end. That would be 15 people. That's all the changes in the cost for housing, transportation, food, and the Rocketeer fees. That's where those come from.
To note on that, I would raise. I think it's very important to have one propulsion lead there, not doubting your ability, but whenever you are in competition,
It's a lot.
both of you will be being battered by the judges, and you don't have time to do anything. Um, whenever I was IREC and I was in part of the Avionics, I was doing the entire teams. Like we weren't siloed into our particular thing. We had to do everything, and I never even saw the chief engineer, the project manager, do almost touch anything on the damn rocket the entire time they were there. So again, not doubting your ability, but yeah.
That's a very fair point. We
Can
definitely do
I?
not. Yes, please.
Oh, go. No, good. Finish your thoughts. Okay.
Okay, I was just gonna say that we definitely don't think that 7 is even realistic. It would most likely just mean that a lot of the we're gonna have to contribute a little bit more to bring more people. Please, Jalissa.
Hey, yeah, I was gonna ask. I don't know who's speaking, but
Isabella, project manager.
oh no, I'm sorry. In the room, the one asking question.
Oh,
I just wanted to piggyback on their questions. Is there any plan to at least, I know it's April, and you don't have much time, but is there any plan for subsystem leads who are going to competition, um, or overall just subsystem leads getting cross-trained in other subsystems? I know when I was at competition, when you're there, the day where you have like your poster and like the judges come to you randomly, they don't care if you're just, structures lead. They don't care that you're payload lead. They're gonna ask you questions overall about the system. So, they can ask you whatever and you have to be on top and, answer correctly. And you can't wait for, Matthew to come back from the bathroom to answer the question. So is there any plans, like how are you guys bridging that gap between knowledge?
yes, definitely. That is something we're taking into consideration, especially with the possibility of bringing in a smaller team. One thing that's helping a lot is to get all the members that are going, or at least as many as we can, their certification, at least their L1 certification, because it gives you some context into all, at least the basics of how all the subsystems work. But we're also, we already had kind of an assembly day with the team from Shasta, where most of the team was there, including propulsion leads, the structure, not just the leads also, but members from pretty much all the sub teams, so that we can see how the whole rocket is put together. We will have more of those days when we have the actual, or at least a lot more progress in terms of manufacturing, so that everybody knows everything about, as much as possible, about all of the subsystems. We also, I think, certification has been important for us in that sense. I mean, I am planning to do my L2 before the competition, and I know that Alfred and I want to get our ham radio licenses as well. So that is also something that we're using to work towards that. Yeah, just a lot of working together with as many people as we can on the rocket in terms of manufacturing and assembly for those dry runs before the competition.
Okay. I will say like my um year when we went, the project manager and the chief engineer kind of like printed out our final report, our final like flight report, and we kind of had everyone study that. Are you guys thinking of doing something like that just to prepare for competition? Like, uh, I'm just saying, like, come judge that day, when they come judge you is just you get battered.
Yes,
Um,
definitely. We've seen some of those binders still in the lab of previous teams, which is just the entire technical report, as well as all the checklists for all the teams. We've actually kind of already been studying the previous ones. Obviously, ours is going to be significantly different, but it's definitely our intention to that technical report is um, the due date for that is in May, so we'll have definitely some time for everybody that's going to study that.
okay. I know I dropped. I came back. Office hours like ended quick, but I did have other questions, but also want to leave room for people in the actual room since I'm just online.
Okay. Anybody here have questions? I think we're good in the room, so if you want to
Oh
ask
yeah,
any
I
more
know it's
questions, yeah.
late. Sorry. This is for the analysis group. I came in a little bit late, like 15 minutes late, so I came in like at the end of the analysis group. I just wanted to know, what data are you using, for specifically like the conditions? So like weather data, like where are you pulling that from?
We've been looking into some forums, and it was kind of the consensus like 2 months ago that uh, currently RockSim, you shouldn't put wind data in the rock.
Oh, sorry, you're quiet right now. I can see you like speaking, but you're just quiet.
Yes, we were specifically requested by IREC not to include wind data, just wind data into our simulations, at least for the purpose of our progress reports. But we do have the wind data, and I think you simulation.
Where they get the data from. I'm I'm the one who's doing a lot of the flight sims with. I'm the one with RockSim Pro. So I've been asking Randy for a lot of help with that. But yeah, he's pointed out to me resources to get wind data. But yeah,
What about like temperature?
yeah. Temperature. The current simulation was 95 degrees Fahrenheit. That's just looking at provided by Ezra.
Okay, okay, cool. Thank you. Um, and then I had other questions too, but it's for like for the overall team. How many how many tests are remaining overall?
Yeah. Uh, recovery as to avionics one, um, payload uh, for payload on the biological side two, on the structure side. Um, I can think of three right now. It is a lot of testing.
Okay, so you still have like subsystem testing. Um, do you have how many integrated tests do you still have?
I'm sorry.
How many integrated tests do you still have?
Yeah. So uh, like ground testing and dry runs. Yeah. Um,
Yeah, so like more than one subsystem.
yeah. Yeah. Uh, I mean, it it depends on the manufacturing, but we are definitely aiming to do this 2 weeks before competition, especially just a full assembly. Um, we've heard stories of common stories of assembling it for the first time at competition, more than one year. So yeah, we're aware of that, and yeah,
So
trying to do
those,
better.
no, thanks. Those like unit tests or subsystem tests, do you guys have like a timeline on how those are going to be like conducted over the next few weeks? Like, does that still give you enough time before competition to like feel prepared? And are you still gonna have time to do your integrated test before you finish your subsystem test? Or sorry, finish your subsystem test as well as have time to do your integrated test.
It is definitely a tight timeline. We do expect to have at least all the critical testing completed before May. We're waiting on some of the parts, namely the airframe. We're still waiting on some of the parts for some of the testing, but we do still expect that to be completed at most maybe the first week of May. And as far as integrated testing, or specifically those that include multiple subsystems, mainly that's going to be recovery and avionics when we do ejection testing. And that to happen sooner rather than later. We have most of the components that we need for that. Um, so in a sense, I would say yes. We believe that we have enough time to complete all critical testing and manufacturing.
Are you worried about? No, sorry, go ahead.
Sorry, Julius, I'm gonna interrupt, but I think what you're trying to get at is that it's very valuable to have every sub team identify every test that they might have to do or need to do, along with every part of the manufacturing beforehand and after whatever needs to happen, and report that to the project manager, so that instead of this like block Gantt chart that you have here, it shows what out of all the tasks that need to happen, what has done and what when you plan on like scheduling the other tasks. And in particular, if there's a possible like what particular test is like the long pole, what's like the one thing that may choke the entire project.
Yeah.
Because like one thing is not identified yet. And so I think she's kind of trying to poke that it's important that every sub team, reports to y'all and says we need to do all these things and you schedule everything out to show what thing is the possible blocker for the entire project. Because if everyone's ready except for one team, then like y'all are cooked. Like that's it, done.
Critical fail.
Yeah.
Yeah, I was also gonna say like, are you worried about delays? Like, have you figured out, if this structure test gets delayed to like, I don't know, end of April, how does that affect the team? Can you go to competition if that structure test isn't done? Can't, if it doesn't get done, is there a way to like simulate it again and have that be like what you present in your technical report?
I will say that we're definitely on track to meet all of the required testing by the competition officials. Um, we have kind of, and this is taken some inspiration from one of the teams that they did. Instead of an exact Gantt chart, they did kind of a road to spaceport, where it's more so a spreadsheet of all the things, like you were mentioning, all the tests that have to be done, but not just tests, also manufacturing, really everything that has to get done. Um, we do have our spreadsheet with that. That's kind of mostly where these tasks came from. This is a bit of a summary of those tasks, but I would say identifying the most critical ones is mostly recovery and avionics, and we are on track to meet those goals even before the end of April. That is pending on getting the necessary components, which we are still working on. We're a little bit limited in terms of getting everything here, but with lead times that we're expecting, we don't anticipate that to be a problem. At least not a critical problem.
Okay, thanks.
biggest thing.
A lot of
Air decay was really ambitious.
a lot of our issues were related to the motor. The motor that we had selected was, quite frankly, not a good or even viable option. A lot of things would have had to happen, and we got this feedback from the Ezra safety reviewers as well that a lot more would have to go into protecting the structure with such a powerful motor. Switching down to 10K COTS category, the motor issue is almost entirely eliminated. We picked a motor that was already in stock, so that timing is going to be less of a problem. And scaled down on some of the SRAP projects, at least some of the ones that were going to be the most critical. For example, not implementing the air brakes anymore. And really just making sure that the rocket that we have has a lot more manufacturing processes that are simple and not as time consuming. I would say those are the biggest changes that have been made. It is basically a whole new rocket. While we're still reusing some of the internal components, the scope has changed dramatically to something that is much more manageable within the time frame and the experience that the team has.
Questions? Anyone online? Well, thank you all for coming. Thank you all.
Nobody wants to see the recovery. Sure.
I have plenty of questions, but I didn't want to. I want to talk to them.
You're a really good project manager. You answer things very politically. How much? I have a question about mass. I feel like it's a thing that'll make or break the rocket in terms of the motor you guys are using. And it was only like one team that talked about the mass budget they had, and I think I wrote that payload had 5 pounds, and like nobody else said anything about it really.